Okay, so I'm Eryk, and this is the idea of Profunctor user interfaces. So Profunctors we all know and love is a type class that is covariant in one type parameter and contravariant in the another type parameter. And please raise your hands if you know what a Profunctor is.
That's already up.
Okay, cool. So what we can do with Profunctors is we can do the die map, which maps covariantly one end and contravariantly the other end. And please raise your hands if you know what the Profunctor encoding of optics is. Okay. So Profunctors are very useful. For example, they can encode Profunctors. So there is an isomorphism between the explicit encoding of optics such as adapters, lenses, prisms, and something I call polymorphic Profunctor modifiers, which are basically functions from PAB to PST for an arbitrary Profunctor P. It's worth noting that this is a polymorphic function, so we can rely only on the methods from the Profunctor type class, and we don't we cannot use any specifics on the underlying Profunctor. And what's good about this encoding is that it composes very well because it's basically a function, so we compose them as functions. So adapter is an example of polymorphic Profunctor modifier. So in explicit encoding, adapter is two functions from S to A and second from B to T, and we can just express them using the dmap. For lenses, we have getter and setter functions. And as long as the Profunctor has additional method called first that enables us to carry some additional context throughout the Profunctor, we can use it to bypass the whole of the lens and apply the setter method at the end of the Profunctor as depicted in this example. With Prism, we need to have co-Cartesian Profunctor instance, which has the method left, which allows us to conditionally bypass the Profunctor for the left or right case, as in this picture. And polymorphic Profunctor providers compose as functions do. So here we have examples of 4 composed optics. 2 of them are prisms and 2 of them are lenses, and they greatly compose and think about the constraints that are needed is that these constraints simply add in the type signature. And also Profunctors are useful because of ability to encode arrow-like computations. So if we pick the arrow choice from the Haskell arrow package, add dmap function to it, subtract R and ID functions, we end up with something very interesting. So by introducing dmap, we enable data plumbing between the arrows. It excludes maybe some instances as compared to arrows, but this should not be the case for the classes that encode some notion of computation, because it's hard to imagine a computation without being able to do the dmap. And if we eliminate R, it disables data plumbing as first-class citizen, but still we have this data plumbing as a second-class citizen using dmap function. And on the other hand, it includes more instances. And the same applies to the ID function. So what we end up with is the arrow-like type class, which has some disabled power as compared to arrows, but has enabled more instances. And it for sure has simpler laws as compared to arrows. So what is required is dmap left second and compose functions, and what can be derived is the lmap, rmap second right, and fan operators known from the arrow type class. So we can see that Profunctors are a common fabric for both data and computation structure. So arrow structure computation and optics structure data, and all is based on Profunctors. So why it's technically not true in the Haskell ecosystem? So first of all, Profunctors as a fabric for optics were discovered late. So we had concrete explicit encoding of lenses, and in 2009 we had the van Laarhoven encoding proposed, and only in 2017 Profunctor encoding of optics was published. Also, Profunctors as a fabric for arrows is not Haskell mainstream for historical reasons. So Haskell arrows package from 2001 predates the Profunctor package, which was funded 10 years later. So the control arrow module made it to the base in 2005, while Profunctor is not in the base to this very day. That's why arrow class is not likely to become a subclass of the Profunctor class in the future. But Profunctor encoding of optics is the default one in PureScript ecosystem. So in Haskell they were late about 10 years, but in PureScript ecosystem, optics are based on Profunctor, and it happens in PureScript Profunctor lenses library. Also, Profunctor's encoding of arrows is the default one in PureScript. Luckily, in a sense, PureScript hadn't got arrows earlier than Profunctors, and when we got Profunctors in PureScript, arrows seem not longer necessary. So in PureScript ecosystem, we don't even use the term arrow, we just use the Cartesian strong Profunctor, which is equivalent. So, Profunctors model both data structures and data flow. So can Profunctors model UIs? It would be nice because it would be declarative and interactive owing to the composability of Profunctors. It would separate business and presentation owing to optics, which I will show later in this talk. It would require only a basic building block that supports demap, left, first, compose, and some other functions. And would that be the viable alternative to functional reactive programming, virtual DOM, or the Elm architecture? So how about PureScript web UI framework based on Profunctors? So the library Bambik, which is the prototype implementation of the idea, and it defines the UI data type, which is basically an effect that returns two functions. First is a function that presents a value to the user, and the second one which listens for input from the user. And this data type instantiates Profunctor, strong, choice, semigroupoid type classes, and also some additional ones like endo Profunctor, some Profunctor, and zero Profunctor, which I introduce later in this talk. The only constraint is that the underlying effect must be of type applicative. So endo Profunctor is a generalization of the endomorphism or endo function, which is a function from A to A, and which is basically an instance of the monoid. So here we have something similar to monoid. This is something for appending PAAs into single PAA. Some Profunctor is quite similar, but it takes two PABs and appends them to the single PAB. And we have zero Profunctor with P0 function that is the identity element for the psum function. So UI web is the UI instantiated with the web underlying effect, which is basically an effect that is capable of building a document object model in web browser. And the basic building blocks would be text, which is web UI taking string and returning anything of any type, which is equivalent to saying that it doesn't produce anything because it's now related to the user input. And then we have text input, which is web UI, which takes a string and returns a string provided by the user. The button, for example, is web UI, which takes an A of arbitrary type A, waits for a click, and once it's clicked, it gives back the value of type A. And the same applies for other elements of HTML documents. So plain HTML is possible with UI web. Here is a simple example. So we can see HTML elements, and all is good together with some do that does psum function composition powered by PureScript qualified do feature. Material design components are also possible with UI web. So for example, we have field text field, which is web UI taking string and returning string We have contained button taking A, returning A, and so on and so forth. And the example is here with MDC card, MDC caption, MDC text field, and MDC button. And it's glued together with sum, I already mentioned, and semigroupoid do, which does the composition known from semigroupoid via the pure script qualified do feature, so that the data flows go line by line from top to the bottom. And data structures are enabled by endo-do. So here we have a form that uses MDC UI, and it uses two lenses, short ID and unique ID, which are lenses from string to order. So what happens here is that we have field text field, which takes string and returns string, and is kind of lifted by this optics of lens so that it operates on orders. And once we have two UI elements operating of orders, they can propagate the data back and forth so that the whole form gets populated with data being input. Data flows are enabled also by the semigroupoid do and sum do composition. So here we have example again with MDC UI components, and we have it's glued with semigroupoid do, so the data flows line by line. So first we have a web UI which takes an order, and the order comes to the contain button. Once it's clicked, the order goes further, and then we have the authorization, which is a lens that turns order to the order summary. The order summary is here printed as text. The user is asked for authorization token, and this authorization token is mapped again by the lens to authorized order, and authorized order go to another step, which is order submission, and order submission accepts authorized order and returns the Boolean status of the operation. And finally, we have a prism that is triggered once the status is error, and only then the MDC snack bar with proper information to the user is displayed. Otherwise, the default message is presented to the user. So business and designs are orthogonal optics, and as we know, optics is just a function from PAB to PST. And when we're dealing with the business, design is transparent. That's why we abstract over the instance of the Profunctor, and we do the optics for all Profunctors. So we use lens, prisms, traversals, and so on. On the contrary, while we're dealing with business with design, business is transparent. So we use different kind of optics, which I call ocular, which abstracts over the data it takes and returns, but it uses specifics of the underlying Profunctor. So business and design separation is very clear. We can have business in one module, the design system in the other module, and we can import it in the UI and mix the two. So we mix the MDC card and text field with business first name and last name optics. So building complex UI is also easy. It involves only design system basic building blocks and oculars. It involves business lenses, prisms, traversals, and so on. The composition of building blocks is easy with endo-do, sum-do, and semigroupoid do blocks. And we also need some glue code to complete the picture. And this is the example of oops. So this is example UI. It's MDC. So we have input of different types. We use lenses and prisms to model the business logic of the form. We use basically all the features of the library, and it's.
Huh?
Yeah, and this example application is backed by this code. Oh, it's very, very... I don't know if it's visible enough, but it's very concise in terms of code size. So each line represents more or less one widget, and the whole design and the whole business logic behind the form is contained in this roughly 100 lines of code. Sorry. Okay, so to conclude the talk, Profunctors seem suitable for UIs, at least for specific classes of UIs. They're good for both dealing with data structures and data flows. They clearly separate business and design. They are very declarative and reactive. They provide easy mental model as well as simple API. And I think this is worth further research and development. And I will be happy to answer any question. Thank you very much.
Thank you very much, Eryk. Okay, we have a first question.
Could you elaborate a little more on the difference between endo composition and semigroupoid composition?
Sure.
Because they seem to have similar types.
Okay, so endo composition is used for forms, web forms. Sorry. Okay. Where the propagation of data is that we have multiple lines glued together with endo, and output from each of the part of the UI in this do block gets propagated to all other elements of this form. So it's like editing in place a data structure. The other way of composition, like sum, is like fan out. So I duplicate the input and give the same input to all of the underlying UI elements, and then collect the results from all those UI elements. And semigroupoid do is just a chaining we know from the category, because semigroupoid is basically a category without ID function. So it does step-by-step execution.
Okay, so endo is for multiple things with like a product state, if you have a product of...
Yep.
And semigroupoid is about like different screens.
Yeah.
Okay.
Semigroupoid is about data flows, and endo is about data structure, I would say.
Hello.
Hello.
So first of all, thanks for this talk. It's quite different from. It looks quite different from the normal model view update framework. So it's not really a question, but I'd like to interest you in releasing it under Haskell JavaScript backend. We're trying to have as many possibilities as we can, as many frameworks as we can to gather more users.
Yeah, so we need to talk to, for sure. Yeah.
Okay, maybe last question.
Thanks for the talk. My question is, would you have any idea of how to sell this powerful concept to a software shop where people are scared of mathematics?
People ask for what?
People are afraid of advanced concepts, like even sounding like Profunctor or something like this.
So you allude to the abstract notions we used here, like Profunctors, which are maybe not approachable for software developers?
This kind of software developers who are not into category theory, who are used to like Java, things like that.
Yeah, I think that, well, first of all, I don't know. But second, I think it could be made very approachable, more approachable for, let's say, newbies in the functional programming and category theory. This is just a first step. It was just a research project to find out whether it's feasible. And I believe there will be further steps in the future. So I'm open to, to make it more approachable to everybody.
Thank you.